Richard Feynman was one of the most brilliant theoretical physicists of the 20th century. He won a Nobel Prize for figuring out how electrons interact with light. But throughout his career, he kept a specific number up on his wall, a number that bothered him constantly. 1 divided by 137. He called it a magic number. Today, physicists know it as the fine structure constant. It acts as the central mathematical pillar of quantum electrodynamics, dictating the exact strength of electromagnetism. It tells us precisely how light interacts with matter, an absolute prerequisite for physical existence. To understand why a single number holds so much weight, take a close look at your own body. If you peel back the layers, you find a dense mix of organs and fluids. Zoom in further, and those organs are built from billions of individual cells, each housing microscopic machinery like ribosomes and mitochondria. Those parts are composed of molecules like DNA and proteins. And chemistry tells us that all of those complex molecules are built from just 92 natural elements. But if you go even deeper into the subatomic world, the picture gets starkly simple. Every atom of those 92 elements is just a mix of protons, neutrons, and orbiting electrons. Look closer at the protons and neutrons, and they are made of smaller particles called up and down quarks. Humans, trees, and planets are, at the very bottom, nothing but different arrangements of quarks and electrons, glued together by a handful of fundamental forces. And here is the problem that bothered Feynman. Every single interaction between those subatomic pieces is dictated by specific numerical values, like the fine structure constant. These are known as the constants of nature. We have to measure them with experiments because our physical theories cannot explain where their exact values come from. Yet everything making up human physical reality is entirely dependent on them. Because these numbers appear arbitrary, we have to ask what would happen if things were different. If we tweaked the value of these fundamental constants by even a tiny fraction, how would the universe change? We can actually test this. Teams of astrophysicists translate the complicated equations of physics into code. Using supercomputers, they build synthetic universes. They input the physical constants, press go, and watch simulated galaxies form over billions of digital years. These simulations track the flow of gas and the intricate dance of matter in expanding space. They verify that under our exact physical rules, mass successfully clumps into protogalaxies. Inside those digital models, stars ignite, live out their lives, and eventually explode, forging the heavy elements required for biology. Running these models gives us a baseline. It proves that the precise values of our physical constants are the singular reason we have complex chemistry and structures, instead of a sterile void. Now we can start to play with the settings. Let's look at the relative mass of subatomic particles. In our universe, a down quark is slightly heavier than an up quark. This specific weight difference allows neutrons to decay into protons, filling the early cosmos with the hydrogen necessary to eventually form stars. If we alter the mass of the down quark to make it slightly lighter, the process stops. Neutrons no longer decay. The Big Bang produces an inert ocean of neutrons. No nuclear fires burn, there is no periodic table of elements, and life never begins. We see the same extreme sensitivity on the macro scale. Consider the gravitational constant, the force drawing matter together to form planets and stars. If we slightly increase the strength of gravity, matter is rapidly pulled into numerous black holes immediately after the Big Bang, locking away the atomic material required for complex structures. If we make gravity slightly weaker, the universe simply expands into a rapidly thinning soup of hydrogen gas, too diffuse to ever form a galaxy. Even staying between those two extremes requires a razor-edge mathematical balance. The lifespan of a star is dictated by gravity squeezing its core until nuclear reactions ignite. Squeeze too hard, and the stellar reactor burns through its material in a flash, denying life the billions of years it needs to evolve. Squeeze too weakly, and you get immense balls of cold, cooling gas. Altering the mass of a quark, or the strength of gravity, triggers an immediate systemic collapse. The physical operating system of the cosmos crashes, rendering the universe sterile before it can ever produce life. We can run the exact same stress test on the variable of time, using a component of the cosmos we have only recently discovered: dark energy. This is the force dictating the expansion speed of the cosmos. For us to exist, the universe had to follow a strict chronological schedule. In the early universe, matter had to dominate over dark energy. This dominance steadily slowed the expansion of space, giving gravity the necessary time to draw dust and gas into clusters. If the universe had been born with a higher value of dark energy, space would aggressively stretch before matter ever had the chance to collapse into stars. Individual hydrogen atoms would find themselves entirely trapped and alone in the cold, empty darkness. When scientists survey the vast multitude of hypothetical universes by mixing and matching these different physical constants, the resulting data is clear. Almost every possible combination produces a dead, sterile universe. Out of millions of possible permutations, ours is the exception. We live inside a staggering statistical anomaly, a perfect architecture that has survived over 13.8 billion years, precisely because it permits human consciousness. We know exactly how perfectly balanced the universe is, but that leaves us with a much deeper mystery. Why are these numbers so flawless? There are a few different traditional explanations. Many physicists hope for a unified theory of pure mathematics that naturally dictates these exact values. Others point to the anthropic principle, arguing that this extreme fine-tuning implies a divine creator who set the parameters specifically for us. But Oxford philosopher Nick Bostrom offers an alternative concept. He evaluates our own technological trajectory. As human computing power exponentially increases, our ability to simulate complex environments grows right alongside it. Eventually, future supercomputers will simulate atomic structures so flawlessly that a digital universe becomes indistinguishable from a physical one. When that happens, conscious beings will emerge inside the code. They will think, feel, and experience a full reality, unaware they are running on a server. If simulating conscious life is an inevitable technological milestone for any advanced civilization, they won't stop at one. They will run billions of variations. Statistically, this means base-level reality is incredibly rare, while simulated realities are overwhelmingly abundant. If we follow the simple laws of probability, it is vastly more likely that we are already existing inside one of those billions of simulations than in the single original base reality. It is a difficult concept to reconcile with our senses. The weather, planetary orbits, the warmth of the sun, and our own biology all feel deeply organic, but under this framework, all of these are merely the elegant execution of digital instructions. This provides a logical explanation for Richard Feynman's magic number. The fine structure constant, the speed of light, the exact mass of a down quark, these are not mysterious cosmic coincidences. They are the intentional, perfectly calibrated base parameters dialed in by an external architect. In this view, the mathematical precision required for our existence is the signature of a deliberate, programmed output, the work of a great programmer.